Okay, so you might remember that we did hypothesis testing a couple of weeks ago, and we were focusing on chi-squared mostly, but there's a new type of test I want to have a look at with you this morning called the t-test. Now, the t-test is very good for looking at averages. I don't know if you remember exactly, but the chi-squared was very good when you were counting things like, oh, you have 2 of these and 3 of these and 4 of these, whereas the t-test is really good when you want to compare averages. So like a simple example might be, maybe you're in the lab, you're growing some plant, for example. There we go, you grow a few of them. And then let's say the average height, maybe the average height is 12 centimeters, for example. And then you're growing another plant, but the difference this time, maybe you give the plant some, I don't know, some type of new fertilizer perhaps, and maybe the plant might grow 13 centimeters. So we would like to know, is there a significant difference between the two? Or is this only a little bit extra and it's kind of due to chance and not really a genuine increase? So just before I go on, I was just wondering, do you have any other examples maybe you can think of from biology where it'd be nice to compare the average from 2 groups? So you could think of an example from medicine as well. Now, if you don't want to say it, you can type it. I'll just open up my chat box here. Okay. So what do you think, David or Sabrina, or anybody for that matter, if you want to type in an example? Can we think of anything in medicine or biology where maybe you'd like to compare 2 different groups?
I'm still thinking.
A little bit too early for examples, huh? I'll give you another example just to help get your mind going. So like one example, I think with column in biology, have you talked about cholesterol?
Yep.
Yeah, and you probably know that there's medicine to treat cholesterol. What unit do you measure cholesterol in? It's like grams per liter, is it? Or milligrams per liter? Did you talk about this?
No, we just talked about the structure.
Just the structure of it, yeah. We'll just say, for example, it's milligrams per liter, and here we have maybe milligrams per liter, for example. So you might want to be comparing 2 groups. The first group has no drug, and then maybe the second, and that's called a control group, and maybe the second group receives some cholesterol fighting drug, and you want to see if the cholesterol is different, if it's lower. So before I go on to the formula, I'll just give you one more go at maybe imagining up an example for me. So what about you as well, David? Can you think of any example?
Not really. Can I use enzymes? Presence and absence
Sure.
of enzymes?
Yeah, absolutely. Enzymes. So what example did you have in mind with enzymes?
Effective enzymes on, I don't know, like a substrate.
Yeah, good, yeah. Yeah, you could have you could look at 2 different enzymes and how they affect the substrate. So you could measure something about the substrate, and then you could see what the effect is with enzyme A and then with enzyme B, and then you can compare and you can see if they're different. So anyways, we can imagine some examples. You know, you could be looking at diabetes medicine for controlling sugar. You could be looking at some medicine for recovery from flu. There's so many examples that you can think of in medicine. It's mostly about testing how effective medicine is. So you might recall that we have these 2 terms called our null and our alternative hypothesis. So when we are looking at our t-test, the null hypothesis is always that the average for the first group is the same as the average for the second group. And the alternative hypothesis is that the average for the first group is not the same as the average for the second group. So that's our hypothesis test. It should remind you a lot of the chi-squared test. Okay, so in the chi-squared test, we had our chi-squared formula. And in a similar way, for our t-test, we have the formula for t. It's a little bit complicated. I mean, it's not too bad. It's a little bit complicated. So I'll just give you a few terms. So in our first group, and there's our second group, we'll say there's N1 participants in the first group, N2 participants in the second group. The average for the first group, we'll call it X1, and the average for the second group, we'll call it X2. Standard deviation, we'll call it S1. Standard deviation, we'll call it S2. And the t-test is going to be the difference in the two averages, 1 and 2, all over this term called SP, and I have to give you a formula for that, square root 1 over N1 plus 1 over N2, and then the SP formula, that's a term called the pooled variance. It's just a calculation where you combine the two standard deviations into one standard deviation. So that's N1 minus, now it's kind of a complicated formula, N1 minus 1, S1 squared, plus N2 minus 1, S2 squared, all over N1 plus N2 minus 2. Okay, I'll just give you a second just to copy this down, and then I'll scroll down. We'll have a look at an example with some numbers. And the other thing actually I'll give you, so just like with just like with chi-squared, we had a table, look up the degrees of freedom and so on. We have degrees of freedom and a table as well for this one. Degree of freedom formula is not too difficult. Degrees of freedom is actually this denominator here, N1 plus N2 minus 2. And let me paste the link for you into the chat box where we can look up the degrees of freedom. So if you have a look here, can you tell me which column do you think we'll be using? You see there's a 1, 2, 3, 4 columns of values. If you think back to your chi-squared test, you can probably figure out which column we're going to use. What do you think, guys? Which one would it be? The 0.10, the 0.05, the 0.025, or the 0.01? Oh, couldn't quite hear you. Say that again.
0.05.
Yeah, exactly. Yeah, 0.05. Good job. Okay, so that's the idea. I'm going to do an example now. And it's the usual story, like with the chi-squared. If your t is too big, you reject. And if it's not too big, then you don't reject. Okay, let's have a look at an example here. Let me just scroll down to the example I had. Yep. Okay. Can I scroll down a little bit, guys? Or do you need a second? Yeah, okay. Well, maybe I'll zoom out just a little bit so we can still see both there. Yeah, great. Okay, so let's have a look at my example. So I have two sets of data. In the first one, let's say I have 249 observations, and in the second one, I have 79. In the first group, let's say the average is 20.1. And then in the second group, we'll say the average is, I think we have here 30.5. Now, it looks like they're very different, but we don't really know if they are because we haven't said anything about the standard deviation. So for the first group, it's 6.4. And then for the second group, we'll say it is 6.1 then. Okay, so now that we have our info, we can do our calculation. I'll just make up an example. Maybe what we're looking at here, this could be something like no drug. And then maybe this could be something like a new drug, for example. And maybe what these represent here is how many days, or it could be, let's just say it could be something like blood sugar, you know, something, or cholesterol, whatever, something bad. It doesn't really matter, you know. Let's do our calculation now. Okay, so T, the first average, minus the second average, over, now I'll leave a little spot for my SP, I'll have to calculate that separately, square root 1 over N1, 249, plus 1 over 79, and then we'll put the SP, I'll pop it down, if I can squeeze this down here, SP on the side here, N1 minus 1, okay, so that's 248, times S1 squared, 6.4 squared, plus N2 minus 1, that's 78, times S2 squared, 6.1 squared, all over N1 plus N2 minus 2. Is there any chance that you two guys have your calculator handy?
I got 129.45.
Oh, that's super quick. Thank you. What's it? 129.45.
0.45.
That seems believable because these are quite big numbers on the top, aren't they? 30. Yeah, okay. It seems believable. 129.45. Super. And then if you could bash that in, let's see what we get here. Are you typing it in, Sabrina?
Yep.
Great.
Hello.
Hey.
Sorry, my Wi-Fi was weak. It's Priscilla.
Oh, hey, Priscilla. We're just looking at t-tests.
Yes.
It's a hypothesis test that we're doing, kind of builds on the chi-squared. It's a way for testing if two averages are the same from two different groups. So
So I got a negative.
Yeah.
Is it like logical?
yeah, of course, negative's fine. Yep. Yeah, negative's fine. What you got?
Negative 0.622.
622. Yeah, negative is fine. Can be positive or negative. So let's go check our tables. Let's open that up here. Okay, so actually I never wrote this down. What's the degrees of freedom for this one? It's quite large. It's 249 plus 79 minus 2. What you get for that one now there, Sabrina? And I'll just look at the tables.
326.
Yeah, okay. Now, you notice that the degrees of freedom stop at 100. Can you see that on the table?
Yep.
That's fine. When you reach the limit of the table, you just use the last value on the table. So that's not an issue here. At 100 degrees of freedom, we use 1.98. 1.984, it looks like. That's the critical value. And we don't care about the sign. Our 0.622 is less than the critical value. So what do you think? That reject or do not reject?
Reject.
Oh, we had a 50-50
You
chance.
don't reject.
Don't
We
reject.
don't reject.
Yeah. Don't reject. Don't reject. Yeah, that's great. Do not reject. So do not reject. So that basically is saying that you have some evidence in support of the hypothesis that the averages are the same for the two groups. So if you were a researcher, what you would say is you don't really think the drug is having an effect, that the average cholesterol, diabetes, whatever it is, stays the same. Oh, good. We're nicely coming up to the time there. Okay, so what to say finally? Well, there's actually many versions of the t-test. I've only done one version of the t-test for you. What this one here, it's an example of a t-test which is not paired. You can have a t-test which is paired. That's a different type of t-test, which is also common in medicine. This is where each person in the first group matches up with themselves in the second group. So for example, maybe the first person is taking drug A in January, and then they take drug B in February. Then maybe the second person takes drug A in January, and they take the drug B in February. That for each person in group 2, you can match it up with themselves in group 1. You know, another example maybe might be, these could be students, and these could be students in first year of university and the same students in second year of university. So there's a pair that you can draw between the two. But with the example I did, it's pooled, it's unpaired, which means all the patients in the first group will be different to all the patients in the second group. Actually, let's see what you think. Which do you think is more common in medical research? Paired situations where all the patients in the first group are the same patients in the second group, or unpaired where all the patients in the first group are different to patients in the second group? Which do you think might be a little bit more common? What do you reckon?
Unpaired.
Yeah, the unpaired
Yeah,
one.
unpaired. Yeah. And the people in the first group are often called the control. They just receive the normal treatment or no treatment. And then the people in the second group, they're called the treatment group. They're the ones that maybe receive the new drug, whatever it is. Okay, so any questions while we wrap that up there?
Nope.
No. Thank you for showing up. We can go back to having a relaxing Saturday. So I'll just pass this Zoom over to the next person.